Today we're going to be talking about logarithms and comparing logarithmic and exponential functions, learning how to convert between the two, and the transformations of both graphs.
Unit 6 is all about logarithmic functions, which are the inverse of exponential functions. Now, exponential functions, as you're probably already familiar with, are in this format: y equals a to the exponent x, a being the base. Now, since log and exponential functions are inverse functions, I can replace x and y. So switch the x and the y, and this equation here, the inverse, is interchangeable for y equals log base a of x. Note that the base over here is the same as the base over there. And also note the restrictions. So a that we're using as the value must be greater than 0 and not equal to 1. So a could be 2, 1/2, 4, any real number that follows these restrictions. And because they are inverse and this equation here is the inverse of this equation, you can actually interchange between the two and convert from an exponential function to a logarithmic function, or vice versa. Now, the log button on your calculator is actually implied that it's log base 10x. So the log button on your calculator would not solve a logarithmic function that had a different base. So say the base was 2, then you couldn't just use the log button on your calculator. And if you also just see log x written on a paper or solve for log x, then it would imply log 10x. So one application of logarithmic functions is converting between a logarithmic function to the inverse of an exponential function. You would do this in order to solve a log function with a different base than 10, which obviously you could just plug into your calculator. So in this first example, we're going to solve for log base 3 of 81. So to do this, I'm going to convert it into the inverse of an exponential format. Now, if you remember, that would be x equals a to the exponent y. So the base of this function is 3, and the base, that would mean the base is always the same, if you remember me saying that earlier. So 3 to the exponent, we don't know, equals 81. That means that the exponent, or y, is 4, which also means that log base 3 of 81 is 4. Let's try another example. So here we have log base 5 of 1/5. I'm going to convert this, so I have the base here. I'm going to make that the base of my power, right, to an exponent we don't know, equals 1/5. Now, down here I put a little extra note. This is just an exponent rule that you should know. So 1/2 to the exponent k is the same as 2 to the exponent negative k. Now, the reason is because if you take something in the denominator to the numerator, then it has an exponent of -1. That's just the rule, and you have to know that. So 1/5 equals 5 to the exponent -1. And the exponent, since 5y equals 5 to the exponent -1, y equals -1. So the answer to this logarithm is -1. This next example, we don't need to solve it, we just need to convert from logarithmic form to exponential. So what I'm doing here is, again, the base, then the exponent, 5/2, equals 32. The next topic of the day is exponential and logarithmic transformations. So on this side, you'll see exponential functions, and on this side, you'll see logarithmic. Now, I've chosen two very simple exponential functions on this side and two, again, simple logarithmic functions, just so you can see the basic shape of the graph. So, as you can see, this blue one is y equals 2 to the exponent x, and on the pink one is y equals 1/2 to the exponent x. And as you can see, when the base of the exponential function is greater than 1, it actually is increasing and it goes up like that. But when the base is less, well, between 0 and 1, so a fraction, it actually goes the opposite direction. And that makes it a decreasing function. So the blue one is increasing, this one is decreasing. Okay? And both of them have a horizontal asymptote of y equals 0, which means that the graph will never pass this line. Oh, whoops. Paper. There we go. The graph will never pass that line, and the domain and range for both of them are the same. X is an element of all real numbers. Y is an element of all real numbers such that y is greater than 0, meaning above that line. And as you can see, this is the general formula of what an exponential function would look like. And those letters just indicate all the different transformations you can have. These two are just what you might call parent graphs, as there's nothing fancy, they're just basic, changing the a value. Now let's look over to this side, and we have logarithmic functions. And again, I've chosen, as you can see, 2, 1/2, 2, 1/2. So the two blue ones are inverse functions. And if you can imagine, so this is the logarithmic one. The other blue one on that side would look like something like that, right? And that means all inverse functions are reflected along the line y equals x. So I put that there, reflection along y equals x. That's important to know because if you already have the points for, say, the exponential function, then you just switch the x and y coordinate. So then it would become, instead of xy, yx, right? You just switch the numbers, and then you don't have to re-find it all. That's an easy way to, just using the coordinates, find the inverse and graph it. So as you can see, this blue graph with log, which is log base 2 of x, is just, again, a parent graph. All of the ones here are parent graphs. And instead of having a horizontal asymptote, like the exponential function, both of these graphs have a vertical asymptote. And as you can see, this blue graph here is increasing, and the pink one is decreasing. So you may notice that both the blue ones increase and both the pink ones decrease. And you can tell whether they're increasing or decreasing from going from left to right. Okay, so you go from negative infinity to positive infinity, and depending where the y values are, you can determine whether a function is increasing or decreasing. Now, if you notice, the domain for both of these graphs is the same, as well as the range. And for the domain, x is an element of all real numbers such that x is greater than 0. That just shows on this side. And range is y is an element of all real numbers. It's also cool to note that these are opposites. So the domain and range switch because they're an inverse function. In these next two examples, let's identify the transformations. So when you see a graph, it's always important to identify the parent graph. So in this particular example, the 3 is what we look at, right? So it's not the a value. Don't get the two mixed up. It's not. This is the a value, and this, though, is the base. And we know that is because it's applied to the exponent. So that's how we know this is the parent graph. 3 to the exponent x is the base graph. And all the transformations are being applied to this graph. Now, we're not going to graph it in this example. However, if you were to graph it, you would find the points on the graph that are on this parent graph, and then you could draw out all the different transformations, but that would take way too long. So you could use the mapping rule, which I've indicated down here. So the mapping rule is x comma y, and it's transformed to x over k plus d, ay plus c. So in this particular example, this is the mapping rule. Now, what I'm going to do is pull out each of the components. So a is -1/2, which means there's a reflection along the x-axis and a vertical compression by a factor of half. Now, d up here is, as you remember, you take it out and it becomes positive, so d is 2. So it's a horizontal translation 2 units to the right. And c is 4. So that means it's a vertical translation 4 units up. Now, as you may remember or recall, this exponential function normally has a horizontal asymptote at y equals 0. But in this example, because the c value is not 0, as in this parent graph, it's just plus 0, which you don't even have to write. Because the c value is 4, and there's the vertical translation 4 units up, that means the horizontal asymptote, which you cannot cross, is at y equals 4. So that's also important to note when you are drawing the graph. Now let's look at this logarithmic example. So first, obviously, identify the parent graph. So the parent graph is log base 5 of x. Now, the first value I'm looking at is 2. So 2 means a vertical stretch by a factor of 2. Then we have -k. And -k just means a reflection along the y-axis. Then we have d, which is 3. Remember, it becomes positive, and that's a horizontal translation 3 units right. And then we have c, which is a vertical translation 1 unit up. Now, the important value in this example is the d value. Now, the reason is because in the example of the standard parent basic logarithmic functions, we saw that there was a vertical asymptote along the line x equals 0, right? So because there was a horizontal translation, 3 units, right? That means that the new vertical asymptote is at x equals 3. And also, as you can see down here, we have the mapping rule once again. This is useful for when you're actually, this -x plus 3 would become the new x coordinate, and 2y plus 1 would become the new y coordinate. Now, I've got on a little sticky note here how to actually calculate the basic coordinates of the actual function. Like, once we have the numbers, it's easy to do the mapping rule, but first you have to get the numbers of the parent graph, which you may not be familiar with if it's a logarithmic function, right? So the first thing to find the x values that you would choose, since this is a log with a base of 5, I'm going to choose multiples of 5. So 1/5, 1, 5, and 25 are the ones I chose. Now, in order to find your y value, you plug in x, right? So I have log base 5 of 1/5, because that's my x value. And in order to find what the y value is, you have to rearrange this, convert this, as we learned earlier, into the exponential form. So we know that the base of this function is 5, so then it becomes the base of the exponential function, so, or the base of the power, whatever you want to call it. So that's 5, and then we don't know what the exponent is, but that's what equals 1/5. So then we know that the y value is going to be -1. We can apply the same principle. I didn't rewrite applying the x, so for every single one, but you can get the idea. In this example, we would have log base 5 of 1, which is rewritten as 5 to the exponent y equals 1, and 5 to the exponent 0 equals 1. So then y is 0. And the same principle is implied for the last two coordinates. So this is useful when you're trying to graph a logarithmic function. You need to know how to calculate the x and y. And also, if you're trying to graph the parent graph, or get the coordinates of the parent graph, so that you can then in turn find the coordinates of the transformed graph. I hope this was helpful.
Thanks so much for watching, and I'll see you in the next video, part 2 of logarithmic functions.